Hello everyone, welcome back. We're continuing on with lesson 2 of unit 6 in Math 10 combined. I've included in unit 6 relations, equations, and graphs, and yesterday we looked at linear relations, and I called it part 1 because everything we learned yesterday we're going to continue to review in today's lesson and build on as well. And that includes how to identify from a table of values whether a relation is linear or not. It includes how to determine which of the two variables we call the dependent variable and which is the independent. And we've got 3 things we want to do today. We're going to continue to graph and interpret linear relations. We want to be able to identify relations as being linear or not based on something called degree. And you are not familiar with what degree means yet. And then I want to briefly touch on the difference between what are called discrete relations and continuous relations. So these 3 terms that I have highlighted are terms that you do not understand yet, most likely, but by the end of the lesson you should. So this is on page 7 of your unit handout, and let's dive right into example 1. Example 1 tells you about a relation between the length of an elastic band and the force being applied to the elastic band. And I'm going to highlight the key idea here in this relation. The length of the elastic band will increase by 4 centimeters for every 2 newtons of force you apply. Well, to begin with, let's just make sure that we understand something here. It's the length of the rubber band that depends on the force. So the length of the rubber band is the dependent variable. This is the dependent variable. And the force is the independent variable. And I want you to notice that this table is set up so that the independent variable is filled in, which is almost always the case. But more importantly, it's filled in showing consistent changes. Specifically, it is always showing that we're going up by 2 newtons each time. Increased by 2 newtons. Increased by 2 newtons. Increased by 2 newtons. So there is a regular change in the independent variable. And that regular change happens to match something that was given in the yellow highlight. It says the length of the elastic band will increase by 4 centimeters every time the force goes up by 2 newtons, which means that this, for the dependent variable, is going to have a consistent change as well. It happens to be a consistent change of 4 centimeters. Obviously, you don't have to write down everything that I'm showing you here, but I think it helps visually if you see what I'm talking about. So to complete this table of values is child's play, which means it's very simple. All we do is we add 4 centimeters to the previous length. So this will be 8 centimeters. Plus 4 is 12. Plus 4 is 16. Plus 4 is 20. And then 24. So the table of values is completed. And the fact that those consistent changes to the variables are there, the variables are changing in a regular, consistent way, or the fact that what I've highlighted in yellow tells you that, means this will be a linear relation. One way to describe a linear relation, or any relation, is to look at a graph. And that's what we are asked to do. We're asked to plot the ordered pairs for this relation on the grid, and then complete the graph. All right, shouldn't be too difficult. The dependent variable is length, so that goes on the vertical axis. We can put the units of centimeters in brackets. And on the horizontal axis, we can put force. And the units in brackets are newtons. The force went up to, I believe, 10 newtons. So a nice scale would be to say this is 0, this is 2, 4, 6, 8, and 10. I'm going to put 12 here because I think we might need it in a bit. The length goes up to I'm looking at my note package here, up to 24 centimeters. Oh, that works out very well. We can say that this is 5, 10, 15, 20, 25 will go here. And I'm going to plot the points. I'll use green to plot the points. You've got colors, feel free to break them out. Doesn't matter. When the force was 0, the length was 4. When the force was 2, the length was 8. When the force was 4, the length was 12. I want you to notice there's that consistent change. When I look at the first green point and I go 2 newtons to the right of it, I go up 4 centimeters. And from that second point, I go 2 newtons to the right and up 4 centimeters. 2 newtons to the right and up 4 centimeters is the consistent kind of a staircase that we're building here. And the slope of the staircase is going to be the same because the base is always going to be 2 newtons and the height is going to be 4 centimeters. So the question says connect the dots or join the points in an appropriate manner. Well, it's going to be linear, so you'll put your ruler down and draw the line that goes through those points as well as you can. And we're done with B. So if you need time to finish your graph, just pause the video here, and when you're done, unpause it and continue. We're going to use the graph now to find the length of the elastic when the force is 7.5 newtons and then when the force is 11.4 newtons. I like to do this whenever we're given these types of questions. It gets students in the habit of doing this, and later on, particularly in 20 level and 30 level math courses, this is part of a strategy that's helpful. I'm going to show this using a table of values. I have my length here. Well, we'll put force first, and that's in newtons, and then my length, which is in centimeters. And what question 1 is asking us is, when this is 7.5 newtons, what is this? And question 2 is asking us, when this is 11.4 newtons, what is this? And essentially all we need to do, and it's not necessarily easy, but basically all we need to do is find a point on the graph that has 7.5 for an F coordinate. Well, that's not a simple task because of the awkwardness of the scale. I just want to put a couple of different arrows over here that I'm going to be needing in some of the work that we do. There we go. So where is 7.5 newtons? Well, 7 newtons is halfway between 6 and 8. So the only reason I have these blue arrows is so that you can follow what I'm referring to rather than me pointing. So that's at 7 newtons. This is at 8. 7.5 is halfway in between, which I would guess to be here. So this blue arrow on the right of the bottom is 7.5. That means I am looking now at a point on there. You know what? I think I'll use blue. I'm looking for a point on that line up here that has a force value of 7.5 newtons. So now what I need to do is read that back to the axis. I need to look over here and read that coordinate. And it's looking as though it's a little bit less than 19. I'm going to say 18.8. And that's my best guess here, 18.8. What about 11.4? Well, it's the same thing. What we need to do is we need to look at 11.4. Well, 11 newtons is halfway between 10 and 12. 11.4 will be almost halfway between 11 and 12. It might be about here. I don't know exactly. I mean, we could break out the drafting tools and the AutoCAD and rulers and ratios and do all kinds of work, but it's not worth it. You'll see why it's not worth it in a bit. So what I am looking at is, if this is 11.4, what's the y coordinate that corresponds to that? So I follow this all the way back, and I'm going to say that's so close to 27, why don't I just call it 27? So I'm going to say my answer here is 27 newtons. Let's take a look at D. What force is needed to stretch the elastic to 13 centimeters? Well, again, it's a case where we have force, which is measured in newtons, length, which is measured in centimeters, and we know one of these values, in this case it's 13 centimeters, and we are asked to find that. So we are looking at the graph at where the length is 13 centimeters. Well, let me turn one of these arrows around. "13 centimeters is right here. Which corresponds to this data point. And now what I want to do is read where it is at the bottom. Whoops, over here. Well, it's somewhere between 4 and 5. Let's call it 4.5. It's probably a little bit more than 4.5, but doesn't matter. Close enough. So 4.5. And that is newtons. What's the disadvantage in using a graph to try to answer these questions? It's difficult because we're not getting accurate readings. So I'm just going to summarize this by saying it's not accurate. A graph is never as accurate as a formula, and that's where we're going now. What's the formula relating the variables? So I want to pause and make sure you understand something here. The goal of this lesson is not for you to become a master at creating formulas. We're going to work on creating the formula together here, and you're going to build to your skills. Your skills are going to get a little bit more useful. And then the next time we do this, they'll get even more useful to you. So this is just an exercise. Don't get hung up on the formula part. First of all, your formula should always be the dependent variable equals. That's how we always want it. Now, stop and think about what the length of this elastic is. The length is 4 centimeters plus 4 centimeters for every 2 newtons of force. And we can go back to the table and I can explain what I'm pulling off here. The length is 4 centimeters plus 4 centimeters for every 2 newtons of force. And I'm going to tweak that a little bit right now and tell you that instead of saying that, what we can do is say the length is 4 centimeters plus 2 centimeters per Newton. When you take a look at 4 centimeters for every 2 newtons, that's the same as 2 centimeters for every 1 newton. And if you give that a little bit more thought, you'll see that the length will be equal to 4, the original 4 centimeters, plus 2 multiplied by the number of newtons. If I figure out the length when the force is 0, I get 4 plus 2 times 0. And that gives me 4 centimeters. If I figure out the length when the force is, I don't know, let's go 6 newtons, I will get 4 plus 2 times 6. 2 times 6 is 12. 12 plus 4 is 16. So when it's 6 newtons, it's 16 centimeters. Let's see if that's right. When it's 6 newtons, the length is 16 centimeters. The formula works, okay? And again, everybody, this is the answer to this question. I don't want you to get hung up on getting the formula yourself. That is not the purpose of this lesson. So there's the formula. Use the formula to find the missing values. Okay, so I'm going to rewrite the formula. The length equals 4 plus 2f. So this 7.5 is an f. Length equals 4 plus 2 times 7.5. You can use your calculator. You should have your calculator out and following along on your own here. And what you get is 19 centimeters. We want to try it for the second one. The length equals 4 plus 2f. So the length equals 4 plus 2 times 11.4. So take a second and figure out what that works out to be. I think it's 26.8 centimeters. By the way, those were the 2 questions back in D or C. Let's see what we got. From the graph, I got 18.8, and the correct answer is 19, and I got 27, and the answer was 26.8. If we want to do the next one where the length is 13, that's a little more tricky because the formula is length equals 4 plus 2f. This 13, I'm going to highlight a few things here for you. This went in for f. This went in for f. However, this goes in for L. And what we're going to be left with here is a very basic junior high-ish question. You have 13 equals 4 plus 2f. You subtract 4 from both sides. And now you're left with 9 equals 2f. When you divide both sides by 2, you get f equals 4.5. Let's move on. You can do the final one on your own. We still have a few more things to cover. It's not that we're going to run out of time here, but I think you get the gist. I will just put an answer in here. If you do use 31.8 and you calculate the force, You're going to have to take the 31.8. I won't show the work, but I'll just do it on my calculator so you have an answer. You're going to take the 31.8 and subtract the 4, and that will give you 2F, and when you divide by 2, you'll get 13.9. So if you are interested in this final piece of this puzzle, this is 13.9. All right, example 2. A 75-gram wooden box is used to hold marbles. The mass of every marble is 15 grams. Complete the table of values. Well, when there's no marbles, the total mass will be 75 grams. If each marble has a mass of 15 grams, then when we go up by 2 marbles, those are marbles, we have to go up by 30 grams. So this is going to be 105. And since the left-hand column is consistently going up by 2, the right-hand column will consistently go up by 30. So we'll get 135, 165, 195, and 225. This will be linear because of this consistent increase. Every new entry on the left goes up by 2 marbles. Every corresponding entry on the right goes up by 30 grams. And I'm just standing here double checking my arithmetic and it looks okay. So this will be linear. And I think you get the gist of it. I'm not going to spend time now graphing this. We're not going to worry about graphing this. That's not the important part of this lesson. Let's cut to the chase and take a look at the equations that are involved. So what is the equation describing the relation? Well, let's use capital M for mass and little n for number of marbles. Turns out that this equation is even simpler to come up with than the previous one. The total mass will be 75 grams because that's the mass of the box, plus 15 grams times however many marbles. I mean, think about that for a second. You have a box that has a mass of 75 grams, and each marble you put in the box has a mass of 15 grams. What's the total mass? Well, 75 grams for the box plus 15 grams times however many marbles you put in there. So we're going to use this equation. I'll rewrite it so we can see it here. M equals 75 plus 15n to calculate some things. However, just to drive the point home, these two things are numbers of marbles, so they are going to go here. Let's do that first. So the mass with 12 marbles will be 75 plus 15 times 12. And you can go ahead and calculate that. I'm getting 255. But it's been a fairly long day. My mind is not the clearest right now, I don't think, so I better double check. 15 times 12 plus the 75. No, I was right. 255 grams. We can do the same thing for the 38 grams. We'll go the total mass, not the 38 grams, the 38 marbles. 75 plus 12 times plus 15 times 38. I could probably crunch that in my head, but why would I want to? 75 plus 15 times 38, looks good, 645 grams. When we look at, I'm going to rewrite the formula, m equals 75 plus 15n, and we look at the number 360, 360 is a mass. It's going to go here. Same with the 390 when we do it. So we can write 360 equals 75 plus 15n. Subtract 75 from both sides. Gives me 285 equals 15n. So then you divide both sides by 15, and that will give you n. $19 marbles. I don't know. You can do the same thing with the last one, but you can see here that this is 30 more grams. That's just something I noticed. From 360 to 390 is another 30 grams. Well, if the marbles are 15 grams each, that must be 2 more marbles, so it's 21. The goal is that wherever possible, you don't actually have to do a graph anymore. You come up with an equation. There are 2 more little things I want to cover. Shouldn't take very long. Let's talk about the difference between what's called discrete and continuous. I'm going to show you lists. There's 2 lists of various relations. And everything in list 1 has something in common. So all of the relations described in list 1 have something in common with each other. And the 3 relations in list 2 have something in common with each other. Let me run through these relations. List 1, the number of golf balls in a box is related to the total mass of the box and the golf balls. How many questions a teacher puts on a math exam is related to the length of time students have to complete the exam. The cost of a 12-inch pizza from Paolo's is related to how many toppings you want on the pizza. List 2, the volume of gas remaining in a tank is related to how far you've been traveling. It's a gas tank in a vehicle. The speed of a runner changes over the course of a 100-meter race, and the height of a horse is related to its age. Not too many people will come up with the significant difference between these 2 lists, but if you want to give it a crack, pause the video, and then when you unpause it, I'll reveal the answer. The answer to the question is that all of the items in list 1 have to occur in whole numbers. I know you can have part of a golf ball, but not in this question. You either have no golf balls, or 1, or 2, or 3, or 4. You don't have pieces of the golf balls, which means the mass changes from one number to another number in chunks. When you look at the second relation in list 1, you can't have part of a question. You have to have no questions, or 1, or 2, or 3. The same with the pizzas. You can't pay for 3.5 toppings. It doesn't work that way. So all of these in list 1 have items that occur as whole numbers. Whereas list 2, all of these things can be anything. The volume can be 6 liters or 12.8 liters. The speed can be 2 meters per second or 2.1 or 2.5. The height of the horse can be 3 feet, 4 feet, 4 feet 6 inches. It can be a lot of different things and not just whole numbers. So how are they different? Some of them are related to whole numbers. And list 1 the variables are chunked by whole numbers. List 2 variables can be decimals. Now, it's a little more subtle than that, but at this level, I think that's the best. We call these types of relations that the variables occur as whole numbers discrete, and we call the second type continuous. So a discrete relation is something where the variables occur as 1 or 2 or 3. A continuous is a relation where the variables occur as numbers that can be any number, including decimals. One final thing I want to look at today, which is called the degree of a relation. This isn't huge, but it's something that you're going to learn about in 10C that you apply in both 20-1 and 20-2, and in the 30 level as well. The degree of a relation is the highest exponent on the independent variable. So I've already set this up so that you know from now on, when you have a variable written as being equal to something, it's the dependent variable. So in this first relation, capital D depends on P, and capital D is equal to 2P minus 12. That means P is the independent variable, and the exponent on P is 1. Oh, that means the degree of this is 1. If you take a look at the 1 to the right of that, x is the independent variable, and x happens to have an exponent of 1. And you're told the degree of a relation is the highest exponent on the independent variable. Oh, okay, so it's 1. This is a degree of 1, too. I know, you're probably saying, so what? We'll get there. Area equals pi times the radius squared. The radius is the independent variable, and the exponent on the radius is 2, which means this is a degree 2. When we take a look at the independent variable here, the independent variable occurs in 2 places, and there are 2 exponents. But you were told the degree of a relation is the highest exponent on the independent variable, so this is degree 3. Now, what's the big deal about this? The final thing we were asked to do in this lesson is to use a graphing calculator to graph all of these and compare the degree to what we see. So this is probably your first foray into using a graphing calculator to graph functions. First of all, you go to the Y button, which is the top left button in your calculator, And you will see y1 equals, y2 equals, all kinds of different things. If you have anything in there, delete it out. Y is always the dependent variable, so we have to enter 2 times p minus 12. But there is no p. We're going to use x. X is the independent variable. So you go 2, and then you're going to hit the x key, and I'm going to highlight it on my calculator. It probably won't highlight very well, but it is right here. Oh, you'll be able to see that. That is the x key. I know it says other stuff, but it's x. So what you're going to do here is go 2 and hit that key, and then we can go minus 12. And what I would like you to do now, so that we're all looking at the same graph, is choose the zoom option, which is the top button in the center of your screen, or center of your calculator, and choose standard, which is number 6. So I got there by going zoom. Do that again by choosing zoom, which is that button, and then I'm going to choose option 6. So what does that look like? This is what the graph looks like. And I want you to note that it's a straight line. I'll just park it here. It's a straight line. If we take a look at the next one, negative 3x plus 6, I'm going to go back to y equals and enter negative 3x plus 6 and graph. What do we notice? It is a straight line. These first two are linear. I'm going to graph now a equals pi r squared, which is entered as y equals pi x squared, and I'm going to choose graph. And I notice that it is not linear. This happens to be called a parabola, or a quadratic function, which you learn a lot about in your 20-level math course. If I take a look at the third one, or the fourth one rather, it is 2x squared plus x cubed, so I have to raise that x to the 3, minus 3. And I take a look at it, and it looks like that. And this is a type of function you would learn about in your grade 12 level course. And it's called a cubic polynomial function. The thing I want you to understand, well, two things, is that when you have a degree 1, it's linear. Let me repeat that. A degree 1 relation is always going to be linear. A degree 2 will always be a parabola. We don't need to worry about that because you're going to study that next year. That's grade 11 math. And a degree 3 is called a cubic, which you would learn about in grade 12. And you would also learn in grade 12 about degree 4 and about degree 5. So the bottom line here is, if it is a degree 1, it's linear. Some questions from the textbook, the ones that start on page 287, 1 to 6, 11, and 12 that you can practice. Again, I'm a little off, I don't think this was the best lesson ever, but I hope that made sense. And hope to see you in school soon. Take care.